The Froude number is a dimensionless number proportional to the square root of the ratio of initial force to gravity force. For a rectangular open channel, the most common expression of the Froude number is V over square root of g times d, where V is the velocity, g is the gravity acceleration, d is the water depth. More generally, for an irregular non-rectangular channel, the Froude number is typically defined as V over square root of g times a over b, with a the cross-section area and b the free surface width, both measured normal to the flow direction. This expression may be derived from both energy and momentum considerations. Introducing the celerity of a small surface disturbance in a canal, the Froude number may be rewritten as a ratio of V over c, with c the celerity of an infinitely small disturbance. This form is analogous to the expression of the Sarrau-Mach number for compressible flow, V over celerity of sound. For Froude and Mach number less than unity, small disturbances at a point can propagate in all parts of the flow. For Froude and Mach number greater than 1, small waves propagate downstream only. The study of two-dimensional supercritical flow in open channels is very similar to the study of supersonic gas flow. The analogy was applied with some success during the early laboratory studies of supersonic flow, when the propagation of oblique shock wave in supersonic flow was deduced from the propagation of oblique shock wave at the free surface of supercritical open channel flow. This photograph illustrates some shock wave in a rectangular open channel. An obstacle forces the flow around the object, becoming supercritical, and shock wave develop downstream of the obstacle. In a compressible flow, the pressure and density depend on the velocity magnitude. The propagation of sound wave in a compressible fluid is comparable to the movement of small amplitude wave at the surface of an open channel, as first discussed in 1781. The combination of motion equation for two-dimensional compressible flow with the state equation produces the same basic equation as for an open channel of incompressible fluid, in which the gas density is identified with the flow depth. Importantly, the analogy between Mach and Froude number is obtained within some limiting assumptions: an inviscid flow, hydrostatic pressure gradient, and a ratio of specific heat being equal to 2. Nowadays, the analogy is seldom applied.